Check, check. Yep. So, hello everyone. Welcome to this talk, which is called Scheduling Cloud with Optaplanner, and AKA How We Almost Beat Academia. During this talk, I'm going to explain to you what we did last summer. We actually participated in an academic competition in the field of operations research, in the field of scheduling computing systems in the cloud. And I'm going to tell you how we actually did. This is the agenda for today. I'm going to explain about the competition, about our implementation of the competition, about the results, and I'm going to share a bit of a future as to what we're planning to do with Optaplanner. But before I do that, I should probably tell you a little bit about myself. My name is Lukáš Petrovický. I work in Red Hat in Brno, and for the past year, I've been working out of Boston, Massachusetts, out of Red Hat USA's office, and I was placed there for almost a year. I had a lot of time on my hands because I didn't have my family there and my friends there, and when you're in a situation like that, you have to go out. You have to go out and explore, right? So when you go exploring, your dreams pretty much come true. I mean, it's been really awesome to see the space shuttle, and I love being there. But also, besides your dreams coming true, your nightmares also do occasionally. And when you've tasted all the food there is, when you've tasted all the beers, etc., when you found your favorite bars, and your favorite places to go to, you eventually run out of things to do with your time, and I really had a lot of time on my hands at the time. So I was looking for something else to do, and at that time, this competition happened, the Icon Challenge for Forecasting and Scheduling. It ran between the end of May and the end of August, and it was a competition for people doing operations research to showcase their algorithms for planning, forecasting, and scheduling. The competition actually had two distinct parts. First part was the forecasting part, which was focusing on forecasting electricity prices based on a past history of their development. I'm not going to spend a lot of time talking about the forecasting part because nobody actually participated in that part. So this is the last time I'm mentioning it, and I'm going to focus on the scheduling part, which is what we actually participated in. So what the challenge was. You should imagine a system of multiple computers connected to a network, a cloud system, and each of those computers in the cloud may execute as many tasks as their resources allow. Each of those machines has a different amount of CPU cores, different amount of memory, hard disk space, etc., etc. So you can fit as many tasks to those machines as those resources allow. Now to the tasks. Tasks have different parameters. They have different resource capacity requirements. So some may require 2 cores, some may require 4 cores. They all have a duration. Each task has a fixed duration, and each task has a earliest start date and a deadline. Tasks, once they're scheduled, once they've started executing, they cannot be interrupted. So once you've scheduled the task, you must finish it on that machine without reassigning the task anywhere else or pausing the task. Now, so far, with a definition like that, it's a problem that's complex, but not that complex. It's essentially a textbook job shop scheduling. And that's boring, right? So we need to introduce a twist. And that twist is a variable power consumption. Each time unit of power will cost a different amount. For example, power may be cheaper in the morning and more expensive at the evenings, or essentially whatever the competition defines for you. And each machine and each task has a different power consumption requirements. For example, machines consume power even when they're idle. So you have to decide if you want to keep the machine idle and pay for the power, or if you want to shut down the machine and pay the shutdown cost. Tasks also increase the power that the machine will consume, so you need to take that into account. And as I already said, the power costs, they differ throughout the day, and as we will see later, they actually differ pretty significantly. So there's some tough questions you need to solve. Which machines do you use? And do you keep them running idle, or do you shut them up and shut them down and spin them up as they become necessary? Which tasks do you put on which machines? That's important, because there may be tasks that are so extremely resource-consuming that there may be only one machine that's able to satisfy those tasks. So you really don't want that machine to be occupied by other tasks that would prevent this extremely large tasks from being executed. This is actually another requirement of the competition. You were forced to create a schedule that executes all the tasks. So if you had a schedule that didn't execute some task, or the task didn't finish inside the time window, that solution would not be accepted to the competition. So there's a picture, and the picture shows the electricity costs that happen throughout the day, right? So you can see that the costs stay fairly the same, except for peaks during the during the evenings. So ideally, your algorithm would take that into account and schedule and try to schedule away those tasks in those peaks. We will see later how we do that. So I mean, trying to figure out an algorithm that answers all of these questions would be very hard because this problem obviously is complex, right? So that's why we have Optaplanner. And I will now move on to talk on a bit about what Optaplanner is. Optaplanner is a lightweight embeddable planning engine that's designed for solving exactly these kinds of problems you just cannot solve by brute force, or problems that are hard to solve by some clever algorithm. It's designed to solve NP-complete problems. It's pure Java. Although there is some XML configuration required, it's mostly Java, and over the past years we have worked towards a point that the XML configuration is mostly non-existent. And of course, as everything that we do in Red Hat, Optaplanner is fully open source. So Optaplanner also is a generic tool. It allows you to model any problem. We've designed it in such a way that it allows you to model any problem. So how does it do that? First, you have some Java code, which is called the entities, the variables, and the values. Planning entities, planning variables, planning values. For example, the planning entity, in our case, may be a machine. And the planning variable may be a task we are assigning to the machine. So what this design does for you is that by providing a list of values for each particular variable, you are able to enumerate for Optaplanner the whole size of your project. For every entity, for every variable, you provide a list of values that variable for that particular entity may have. This sounds like a lot of work, and it really isn't. And I hope to be able to show you that later. Now that you have your entities, your variables, and your values, now that you have your problem defined, you need to have two other things. First, you need to be able to tell how good the solution that Optaplanner is coming to, how good that solution is. You need to provide an objective function, something to say that solution 1 is better than solution 2. So that's called a scoring function, and I will show you what a scoring function in our case does. And then the third part, very important part, is the moves. Moves are essentially a way to transfer you from one solution to another. For example, one move could take a task and move it from machine A to machine B. And the original solution gets a score, the new solution gets a score, and that's how Planner is able to tell if it's progressing. Now, obviously, Planner isn't going to do brute force, right? Planner is only going to try moves that make sense to it. So that's where the implemented algorithms come into. Planner implements simulated annealing, taboo search, late acceptance, hill climbing, et cetera, to be able to avoid the necessity for going brute force. Actually, Planner also implements brute force, but nobody uses that because that's so inefficient. What Planner does here is that it uses these algorithms I described to essentially trim down the state space and try to go only into the branches where it seems that there could be improvements found. What Planner does in this case is completely configurable. There's a myriad configurations for how Planner evaluates the moves and how Planner filters through the state space, et cetera. So this is very flexible. I'll try to show this on a very simple example. The problem is called n-queens. It's not a particularly interesting problem. I'm only mentioning it because it's extremely easy to understand. The problem is you have to place queens on a playing field as you would in chess. So none of the queens can be placed in such a way that they would attack some of the other queens. So they can't share a row, they can't share a column, and they can't be on the same diagonal. So that's the problem. And I mean, obviously, for 4 queens, it's trivial to solve. For, I don't know, 200 queens, not so much. And this algorithm actually is brute forceable. It's brute forceable in a reasonable amount of time. The reason I'm showing this is that it makes it very easy to explain what the entities are, what the variables are, and how the moves work. So you should see the queens as your entities. And you should see the row that the queen is placed on. Not the row. The row. The row the queen is placed on, you should see as a variable. So you have 4 entities, and the columns are fixed. So one queen is always in column A, one queen always B, C, D. And now you only change the rows. So you have each of the entities has one planning variable, which is the row, and 4 values for that variable, rows 0 through 3. Now apparently this means that you have 16 combinations of where the queens could be, right? So what Planner does is that it takes one combination from some sort of a starting solution, and it moves the queen. It moves another queen, another queen, another queen, and each of those, this is a first move, second move, third move, fourth move. And what happens here is that at each of the moves, it calculates a score, right? So here you have essentially 6 hard constraints broken, since the first queen is attacked by the second queen. The second queen is attacked by a first queen and the third queen. So that's 3 hard constraints broken. The third queen, once again, 2 queens, and the last queen is 1 queen. So that's 6 hard constraints. So the score would be -6. Now if you move to the other picture, you see that the scores actually changed, right? No, it didn't. In the third picture, the score is actually changed since some queen, that queen, queen in row B, is now only attacked from 1 queen, which means we have brought the score down from -6 to, I think, -5. I should have made notes there. I'm sorry. I'm doing this out of my head. So essentially, this is what Planner does. Planner will try these moves one after another, and eventually it will come to a move that solves the problem. For this kind of problem, it's very easy to solve the problem, but you may get to a state where the problem may not have a solution. But I will try to show you this in practice, because Planner actually has some very nice examples. So let me move the example window. Okay. So I open the n queens problem, and I load the 4 queens example, and I click on solve, and as you can see, it's done immediately. This is a solution. This is the perfect solution. But okay, let's say 4 queens is too simple, right? So we'll try 16. Click on solve. Once again, it's done almost immediately. So let's go for 100. This will take a while, but not very long.
Why does Optaplanner does moves which are not valid? Because in your second picture, it moved the queen into the position which obviously broke the rule. So why doesn't it skip?
Yeah.
Because it can optimize.
This is actually a very good question. Why does Optaplanner sometimes make moves that break the same conditions it's trying to optimize? It's a very good question. it does that because sometimes you are stuck in a local optima, right? And maybe the only reason to move out of the optima is just try something that seems crazy. And maybe it will lead you to a better place. So this is what Optaplanner can also do. It can break out of the optima using moves that generally wouldn't work. This is a far too small screen resolution. But if I just move it, you will see that all the queens are placed. And I challenge everyone to find the bug. We can do a lot more queens, but then it just won't render. So I can show you it will actually get to a score of 0, which means a complete solution. But unfortunately, you won't be able to see anything. Now you can see that the planner is actually working. It's optimizing. If you give it a little bit more time, it's going to get to 0. Yes, because this is the best score. Optaplanner will try some of the worst solutions. This is the best score, so it will always return the best one.
So one score is the best one?
Yeah, that's the best one, definitely. Now you would see the solution, but because we don't have so much space on the screen, it's not visible. I apologize for that. But hopefully you've been able to see how Optaplanner does these things on this very simple example. So now that we've seen that, give me a moment. Now that we've seen that, let's move on to what we actually designed for the competition. The data model isn't, again, very complex. You have a task assignment entity, one entity for every task. So if you have 5,000 tasks, you will have 5,000 entities. And these entities have two variables. First is the executor, which is the machine that the task will be executed on. And the second is the start task, task start date, which is actually enforced to be between the earliest start and the difference between the deadline and the duration, so that we actually hard code these hard constraints, because we found out that in this particular case it works better if we hard code those. You don't need to hard code them. You can have such a problem that you can make Planner do all this work for you. But we just found out through benchmarking that this works better if it's hard coded. So moving on to the scoring function. We used a very simple scoring function that only consists of a hard score and a soft score. Hard score is the hard constraints that cannot be broken. So if a hard score is not 0, it means that the solution is unacceptable. Why would a solution be unacceptable? For example, because a task hasn't been scheduled. That's not allowed by the competition. Or maybe it's unacceptable because some machine is over-constrained. You've put much more tasks on the machine than the thing could actually handle. So that's why your hard score would be non-zero. Again, if it's not 0, the solution is not acceptable, so you have some work to do to improve your algorithm, improve your moves, to help Planner search better through the state space. Then the soft score, that's actually the actual objective function. That's the operating costs. That's the power costs for all your tasks, all your machines, all your shutdowns, all your startups. That's what the soft score is. And obviously, the lower that is, the better, because we are talking about cost. Now, Planner actually allows you to write your scoring function in a variety of ways. We use the incremental Java score calculator because that's by far the fastest. But if you want to, you can write an easy calculator which doesn't do any incremental stuff, so it's very slow but very easy to write. Or you can use a rules calculator, which allows you to define rules for scores declaratively. It's also very slow, but it does have the incremental benefits. So not everything is recalculated all the time. Why am I talking about incrementality? It's because some of the moves that Planner makes are fairly minor, right? It could move a task by 1 minute. So why would you recalculate the entire scoring function if you know that just a very small portion of it has changed? That's how you improve performance. You make your calculations incremental, which is much harder but also much faster. In our incremental Java calculator, we were able to do, I think, 150,000 calculations per second, which in terms of Planner is actually pretty awesome. With the Drill's calculator, we would have gotten to 10,000 maybe. So you can actually get superior performance when you write all that stuff custom, but you don't need to. Now, coming to the moves. We only use a few moves because not very many more were necessary. We use a move that moves a task to a different machine. We use a move which moves the task in time. And we use a move that swaps two tasks between machines and between start dates. So these three moves we use, and we didn't write any code by hand for this because Planner actually has that built in. It can take your domain model and create those moves for you. So we didn't write a bit of custom code for this. Now, what we did need to write is some shutdown and idle time detection. There were essentially two options for writing that code. First, we could have made shutdown or idle some planning variable with values true, false. This would have worked, and through benchmarking, we found out that it's just so much easier if we don't introduce that, if we don't grow the problem by introducing yet another planning variable. So what we did is we simply took a look at the machine, calculated the actual shutdown and startup costs, and if we found out that they are lower than the idle running costs, we would just shut down the machine, and if those idle costs were lower, we would just have the machine running. This is hard coding something that probably shouldn't be hard coded, but we find out that the performance of the algorithm with this hard coded was just so much better, so we kept it in. Now that we know what we did, let's talk about how we did. There was a public leaderboard where all the participating teams were publishing their results. Essentially, the competition organizers, they published 50 different instances, varying widely in size. Some had 20 machines and 200 tasks. Some had 100 machines and 5,000 tasks. And you were supposed to provide solutions for all of those instances. There was a time limit. I think it was a 5-minute time limit for each instance. So you had to produce some results in this time limit. Each team was ranked on their performance with every instance, and then there was an equation that produced your final result on the leaderboard. Those leaderboards were updated daily as teams were publishing their new better results. So the position of different teams in the leaderboard was actually changing very often. As you can see there, most of the time we were at the second place, sometimes even first. And for some instances, our algorithm was just so powerful that it never left the first place. This happened mostly for some of the smaller of the instances, and why I'm going to get to why that is soon. So the final submission for final evaluation was going to happen with data sets that no one's ever seen, right? The competition organizers had their own instances that they held private, and they would evaluate everyone on these instances. We actually submitted 2 different implementations. of the problem because, and this is why we don't perform as well on the larger instances, is because Planner currently is a single-threaded application. So we simply couldn't be competing with teams who have their not generic algorithms, they have their custom-tailored solvers for this particular kind of problem, and they have those algorithms written in such a way that they can be easily run in multiple threads. So this is a threat for us, and we know that, and we'll get to it. But what we did instead is we ran our algorithm, the two implementations of our algorithm, we ran them in parallel. So we gave each one a different random seed, and at the end of the 5 minutes, we just took the 12 different instances and took a best score that they produced. Because with a different random seed, each of them would obviously produce a different result. This turned out to work very well for the smaller instances. Once again, not so much for the bigger ones. Eventually, when the results were published, we finished in the second place, which was fairly consistent to how the entire competition was going for the 3 months. We sometimes were first, but most of the time we just weren't. Most of the time we were second. And here I want to mention that we were beaten by a team of university-funded researchers whose full-time job it is to work on that. And they were like a team of, I think, 3 or 4 people, and they have an army of interns, students. So yeah, it actually felt very good to come in second after those guys. And it's possible. There was some prize money in the competition, but it's really the time we invested over the weekends and over the long nights, it wouldn't really pay for I think it was 500 euros or something that the competition was paying out. So it's a good income, but it doesn't pay for the work you had to do. So essentially, we by spending weekends and nights on this, we were able to beat 2 other research teams, and we weren't that far behind the first research team. So that made us very, very happy, and we think it shows that Planner is a really capable tool. But let me talk for a while about the 2 implementations. We used 2 different implementations because we found out that some of them perform better when the data sets have more tasks than machines, and the other performed better when it was the other way around. We weren't really able to figure out why that was, but we currently think it was because there was some different looping through the collections, and it turned out that in certain cases, looping over the tasks rather than over the machines was more efficient. I won't go into that. I just want to mention that we gave 2 different implementations because we were able to figure out 2 fundamentally different ways of handling larger and smaller data sets. So the question is where to find those implementations. The first one, my implementation that I was working on, is on the URL up there. That's the one that has no GUI. It's just a command line application. And the other one that I'm going to show in a while is actually an Optaplanner example, so you can find it on their website, on our website, and it's called Cheap Time. The example is called Cheap Time, and I'm going to show it right now. Just give me a second. I'll close this thing.
Excuse me, did anyone else in this competition use Optaplanner?
No, I think they'll start, but not yet. So let me open the example and load one of the instances. Each dot you see over there is a start date of a task, the earliest start date of a task. And what you see here on the bottom, That's the electricity price, right, over time. So what you see is that you would ideally like us to schedule things here, because over here it gets much more expensive. So let's see what Planner can do, right? Now, the different colors, they're the different machines. We have 10 machines in the problem, and each of the lines is a different task. So we have 200 tasks. And you can actually see how Planner's changing things. The rows, they're the tasks, right? So you can see that here, the green machine is actually doing absolutely nothing at the period where it could be doing absolutely nothing because the prices are so high. And you will see that we are also, the first machine on the top, it's also created a space there so that not very many things are executing. But apparently, some tasks just have to be executing at the time. So, because otherwise the solution wouldn't be feasible. So what Planner is doing, it's moving those tasks from one place to another, and it's still optimizing. Here you can see the actual cost as the second number here. You can see it keeps going down, and it will be going down for a very long time. I could have it running like that for the next half an hour. It would keep going down and down and down and down. So this is how it works. This is the second implementation, not my implementation, but an implementation of my colleague. And if you allow me, I'll move back to the slides. There's only a few more. Yeah, what's next? We actually want a multi-threaded Optaplanner. It's very important to us, and we will get there. We already have a prototype. So yeah, that's going to happen, hopefully in the next few months. And maybe we're going to enroll in some other competitions. For example, there's one very nice and very challenging competition on nurse rostering. We already have a proof of concept, but it turns out we don't have as much time now as we would like. So maybe we will submit something, maybe we won't. If you Google, if you look around in my GitHub, you will see the proof of concept. We generally keep those things public, so you can take a look yourself. And of course, there's more. We have a workshop that will show you how Optaplanner works and what it can do. It's at 1550 in A112. We also have a website with documentation and examples. And if you're interested in the competition, there's the problem description and the leaderboard archive, so you can check. Thanks. So you can check on everything I just told you. So with that, I thank you, people, and I open the floor to questions. Yes? Okay, how many people were on our team? It was me mostly, and the lead developer for Optaplanner. Yeah, that's it, I think. I know someone pushed someone commit into the repo, but I don't remember who it was anymore. Yeah.
I wanted to ask is that Optaplanner is using simulated annealing.
Yeah.
And so the second one,
Tabu search. Optaplanner uses simulated annealing, tabu search, hill climbing, late acceptance. We have a bunch of algorithms, yeah.
Why don't you use genetic algorithms? Because for these problems
we did have a proof of concept implementation of GA. We found out in our cases where we experimented with GA, it just didn't work for us. It didn't provide as good results as this does. But obviously, I can't say that for every problem in the world. So at some point, there will be a functioning GA implementation in Planner. There's not one there right now. Any questions? Yeah?
For more complex problems, is it possible to determine that you have already found the best solution, or are you just still getting closer?
So if it's possible to determine if you have the best solution, that's a question for academia, isn't it, right? This will require proof. I don't think it's possible. I don't think it's possible to know if you have the best solution, but some researchers may prove me wrong on that.
Was there any difference in performance between different algorithms, like
If there was a difference between simulated annealing, taboo search, etc., we actually combine those algorithms. We use simulated annealing and taboo search. I think there even at some point was a hill climbing implementation, but it's not in performance. It doesn't affect your calculation count. It affects your scores, though. Some algorithms are just better for this problem than other algorithms. So it takes a lot of benchmarking to figure out what you want Planner to do.
one question, why does Red Hat develop this software? What's the use of it?
Well, first of all, why does Red Hat develop Optaplanner? It's because we didn't really. It's a community project, right? We have a guy working for us who developed this starting in his own free time, and it sort of evolved into something we decided we would at some point be selling. That's what happens. If it's good enough, I think we will at some point start selling it.
Looks good enough.
Yeah.
If I understand it correctly, Optaplanner is sort of like a library.
It's a library, yeah.
Okay, so and you can put there new implementations of UI algorithms for solving the issues.
Okay.
Is it extended?
Are you asking about the UI?
I mean,
User interface?
no. I mean,
Yeah, okay. So whether Optaplanner is extensible so that it would allow you to implement a different algorithm, like, for example, GA? Yeah. As I said, we had proof of concept for GA, so it is possible. It's not exactly easy, but we do want in the future to make it as easy as possible to make your own extensions, to provide your own algorithms. We do intend to do that at some point. So, yeah, one last question, folks.
Okay, do you know about any real-life instances of Optaplanner companies commercially?
I do. They're not public. There are instances, pretty large instances of this being already put in practice, especially in the case of vehicle routing, traveling salesman problem. We do it very well. So thank you, guys. Please feel free to rate me if I did a good job or not. And if you want to talk to me, I'll be here for the entire day, for the rest of the day. So please come and find me. Thank you.